Actually my first Spark meetup, and in fact my first meetup, so it's kind of exciting to be here. I'm actually a postdoc in the AmpLab. I just started almost a year ago. I guess I just started 4 or 5 months ago. My thesis work was in machine learning, in large-scale analytics, sort of more focused on kind of statistical methods, but I also developed large-scale systems. And so today I'm going to talk to you a little about my focus on large-scale systems, and this is going to lead towards the GraphX project. And so everyone's talking about big data these days, and big data brings you more signal, and we're animated. Okay, big data brings you more signal, but it also brings you more noise. And I think this is one of the big issues that we face as we try to develop sophisticated analytics techniques to target big data. And so what I did in my thesis, and sort of the focus today, is to look at big graphs. Sorry, we're having animations. Okay, so big graphs are exciting because they let us understand or squash the noise in our data. And we have lots of them. We have big graphs from social media to science, advertising, and the web. And these graphs essentially encode the relationships between people, facts, products, interests, and ideas. And so the kinds of graphs that we want to think about in an analytics case are graphs that are on the order of billions of vertices and edges. And in many cases, and in fact in most cases, there's lots of rich metadata. So these aren't just graph structures, but they're annotated relationships between people and products, interests, ideas. And so from a machine learning or a data analytics perspective, these graphs are very essential because they help us identify sort of influential people and communities, also influential information. They help us find communities, understand people's shared interests, and they allow us to model complex data dependencies. And so to give you an example, we can look at the task of sort of trying to predict the political bias of users. So imagine I have a collection of users who post or interact with some service. And based on those posts, I might be able to build a very simple classifier, a machine learning tool, to read the content of the post and predict the political bias of that post. And maybe I can't run on all of them, but some of them maybe have some signal that indicates the bias of that particular post. And I can do it for both these users. And then from the aggregate effect, the aggregate signal of those posts on those users, I could then try to predict their individual biases. So the guy on the left is a liberal, and the guy on the right is conservative. So this is great, and I can apply this to a large collection of users that might have politically polarizing comments or interact in a way that actually produces signal. If you think about the reality, most people don't provide politically polarizing comments. So the vast majority of the users, the things I want to reason about, don't have enough local signal to make predictions, right? And so this is where graphs step in, because by looking at sort of the relationships of people, with other things they interact with their community, we can draw conclusions across the graph. And so we can imagine applying algorithms like belief propagation to sort of an induced conditional random field. And this would allow us to make predictions about users for which we have no local signal. It's sort of the power of graphs. But graphs show up in a lot of other contexts. So there's graphical models. So in statistics, we can develop very sophisticated representations of structured data. And it could be things that allow us to reason about the structure of proteins, to look at images and understand their context and what they're describing, and even work in tasks in natural language processing like machine translation. So essentially all of these things rely on graphs. So graphs become sort of fundamental primitive to the way we analyze large amounts of data. Another case where you might see a graph, a particular graphical model, is in language modeling. So this is trying to induce topical understandings of documents and words. And so if I had documents like books, and I had words that occur in those documents, then I can connect the words with the books or the documents when they occur. So the word cat might appear in the book about Steve Jobs, likewise the word apple. And I want to reason about these words and these documents jointly. And what that means is trying to predict sort of latent representations of the words and the documents. It allows me to group them into semantically similar categories. So this could be things like trying to identify how much a particular word really refers to the actual cat or apple versus the computer. Right? Another task that we like to do with graphs is triangle counting. So in this particular task, I might want to take this person in the middle and count how many triangles that vertex is a member of. In this case, that vertex is a member of 4 triangles. And so these triangles sort of measure the cohesiveness of the community. And so I can think of things like a clustering coefficient, which is a ratio of the triangles that vertex is a member of to sort of the degree squared of that vertex. And so the idea is that vertices that have fewer triangles have a weaker community, and vertices that have more triangles have a stronger community. And so being able to identify vertices or users with strong communities, I might be able to target ads more effectively. So another task that we like to look at is collaborative filtering. So here I want to target ads, or I might want to make recommendations about products. And so the classic example is Netflix, right? So if I have a user who's rated a collection of movies, in this case it's a collection of movies I've never seen, I don't know what to recommend for this user. But fortunately in the system I might have other data that relates this user to another user through the movies, right? And so here I have a bipartite graph relating users and movies. And using that graph I can make predictions and make recommendations about what might be a good movie for a user for which I don't have a good recommendation already. Right? And so actually we can formalize that model, this classic Netflix problem, in the form of collaborative matrix factorization, where I can think of a matrix encoding the ratings of users by movies, and I can break that matrix into a bipartite graph. And there's a simple equation here. Actually, it really is pretty simple. So the model for one user can be expressed as just a sum of models for other users. Right? So I can model my interest as a function of the neighborhood of my vertex in the graph. So again, by representing the data as a graph, I can make much better predictions about the interests or recommendations for users. Okay. And then of course, there's the classic algorithm everyone knows about, which is PageRank. Right? So algorithms like PageRank allow us to identify important individuals in a large graph or in a relationship network. And these algorithms have another very simple form that the rank or property of a user can be expressed as a function of the neighborhood of that user. So in this case, the rank of user I is simply a weighted sum of the ranks of its neighbors. And so this algorithm works by starting with every user having the same rank, and then updating these ranks in parallel, and then iterating this process until convergence. Okay, and so there are many algorithms for graphs. I'm not going to go into all of them. There's things in collaborative filtering, stuff for structured prediction, trying to make predictions about groups of things that are related. Tasks in semi-supervised learning, trying to learn things where I don't have any observations. Tasks in graph analytics is things like PageRank or triangle counting. And even basic things like classification. If you look at deep learning and neural networks, those also break down into graphs. So what do these algorithms look like? So if we want to step back and think about how we're going to build systems to support these algorithms and to apply them to very large data, we kind of need to know the structure of the algorithms themselves. And generally, they have the following properties. The algorithm can be expressed in terms of this dependency graph, this relationship between things I'm trying to reason about. There are local updates that my computation for any individual vertex can be expressed just in terms of the neighborhood of that vertex and not the entire graph. This is allowing us to take these algorithms and scale them up to graphs with billions of vertices. And then in most cases, I'm going to iterate that my interests are reflected by my friend's interests, and likewise their interests are reflected by mine. And so I'm going to have to iterate this algorithm until we come to a convergent state. Okay, and so if we step back, the sort of tools we have today for large-scale analytics focus around Hadoop and a particular data parallel model, which I take rows and I transform those rows with some computation, and they aggregate the result into some final statistic, right? And this is a good pattern for a lot of analytics. But if we look at graphs, the structure of the computation is slightly different. In this case, each vertex needs to look at its neighborhood, do something, and change its state. And the parallelism, again, sort of emerges from running multiple vertices at once, right? And there, as a consequence of this sort of need for graph systems, a lot of new systems have emerged. So Google introduced a system called Pregel, which is similar to the Apache project called Giraffe. And then the GraphLab project, which is actually part of my thesis work, also describes a system for dealing with computational large graphs. Okay, and sorry. And so we might ask, how should we program these large graph algorithms? And so what Google recommended, and actually a very good philosophy, is to think like a vertex. So when we try to design algorithms for graphs, we design these algorithms at the vertex level. And so we can kind of capture this idea of a vertex level program in the context of a graph parallel abstraction. And so the graph parallel abstraction works like this. Each vertex corresponds to a vertex program, a user-defined piece of code. And then the graph constrains the interaction of these programs along edges. And so in the case of the Pregel abstraction, vertices interact by passing messages to neighboring vertices. So I write a little program on each vertex, and I pass messages to neighboring vertices. And I use this programming primitive to express my algorithms. And then likewise in the GraphLab abstraction, sorry, and then likewise in the GraphLab abstraction, each vertex interacts with its neighbors by reading shared state. And then parallelism emerges by running multiple programs simultaneously. Okay, and so there's actually there are a collection of high-level abstractions that have been designed or systems to support graph computation. One of the most popular ones is Google's Pregel, and this is turned into Giraffe. And then the project that I had worked on for my thesis was GraphLab. But there are many others. So there's Giraffe, there's Stanford GPS, there's Signal Collect, Combinatorial Blast. So a lot of systems have emerged for defining graph algorithms. And so what I want to do today, before we step into how we're going to approach this in the GraphX project, I want to step back and sort of describe the details of how you might write an algorithm in each of these abstractions. Okay, so first we have the Pregel abstraction. So this is the one popularized by Google. And so here, I'm going to try to write the PageRank algorithm in terms of a little Vertex program. So here the Vertex program describes a computation that lives on the vertex I. And that computation begins by looking at messages sent from neighboring vertices, encoding the rank of those vertices, and computing their sum. And then once I have their sum, I can then take that and update my rank, and then send new messages to my neighboring vertices. So that's the very simple computational model for expressing the PageRank algorithm in just a few lines. By doing this, just like in MapReduce, the system can then execute this in a distributed fault-tolerant way on very, very large graphs. And so if we look at the computational model that emerges, if I want to then run that, the way the system is going to do it is it's going to execute that program on all the vertices simultaneously. Thanks. And then there's a phase in which each vertex sends messages to its neighboring vertices so they communicate. And there's a barrier, and the process repeats. So that's a bulk synchronous computational model expressed in Pregel, and this is how you would write algorithms like PageRank as well as the many other ones I described earlier. And then GraphLab has this very similar model, but instead of sending messages, in this case GraphLab, you just directly access neighboring state. So again, you're going to iterate over each of your neighbors, computing the weighted sum. That's a PageRank update. Then you update your own value based on the result of that sum. And then finally, GraphLab allows you to do one extra cool thing, which is trigger neighboring computation only if necessary. And so this allows us to adaptively schedule and focus computation. And this is something we're also going to be able to do with GraphX. So I want to show you what that means. So here's a use of a probabilistic graphical model. So I'm going to take this synthetic picture of a sunset and try to remove the noise. So you can imagine I took this with a terrible camera. The way I might encode a graph to understand this noise or to reason about this noise is I might say that neighboring pixels are similar. So I expect images to be inherently smooth, right? And so I can encode this relationship between neighboring pixels in the form of a regular grid graph. And so then if I look at this problem, the hard part, the computationally challenging task, is figuring out what happens between the boundaries of regions in this rainbow, right? And so maybe here, it's very easy to figure out that this should be a darker pixel. But when it comes between the boundary of two regions, it's a much harder problem. And so what we'd like is the system to be able to focus computation on the parts of the image that are actually challenging. So here's a video of the actual system running. And so here the system's going to adaptively target the computation first over the entire image, and then later it's going to figure out that the hard parts of the problem are between regions in the rainbow. And we want the system to be able to do this so the user doesn't have to think about that, right? So we want abstractions that can express this. Okay, so by exploiting the graph structure, these graph parallel systems actually can achieve orders of magnitude performance gains. So I go back and look at sort of the speed-ups we get from these systems. Here's looking at a task like PageRank on the Twitter follower graph. So it's a relatively large graph with 40 million users and 1.4 billion links. And so I want to reason about PageRank or some measure of the importance of users. If I compare against a system like Hadoop, we can achieve orders of magnitude gains going from Hadoop to a system like Pregel or GraphLab. And we see this in a lot of things. So we look at triangle counting. This is a number that people have seen a lot, I guess. But so we look at triangle counting on Twitter. I'm trying to find the users that have kind of rich communities. If I look at a system like Hadoop that's been optimized to solve this particular problem using a sort of optimized algorithm, using 1,500 machines, they can compute actually 34.8 billion triangles in 423 minutes. Since the animations are a bit quick here, GraphLab on 64 machines can solve the same problem in 15 seconds. Right? And there's a lot of reasons why this is. It's a C++ versus Java and whatever. The reality is it's because of abstractions. By exploiting the change in abstraction, we can actually show you do a degree squared communication in this case, and we can bring down the communication to linear. Right? So by using the right abstraction, we can build systems that can scale graph computations to really large problems. So that's kind of the summary idea, that taking these specialized graph systems, I can actually solve very large graph problems by exploiting the graph structure. So each of these systems expose some specialized API which allows me to express these complex graph dependencies, and then exploits that structure to speed up the computation. And so now the question we might ask is, why do I need a system like GraphX? And so Reynold is going to explain that.
Thanks, Joey. Let's give Joey a round of applause. And I promise you I won't show you any more math. So now back to the question, why GraphX? Good. If you look at what Joey just showed you, using sort of specialized graph systems like GraphLab, they were able to bring down sort of like the page rank or triangle counting from running in Hadoop, taking a very substantial amount of time to a very short amount of time in orders of magnitude. Of edges, which are relationships between your users. And you can actually construct a graph out of this pretty easily. But what's lacking in, again, all the specialized systems for graph systems is it's very hard to connect a relational database to them. And Spark actually is pretty good at this. You could write a Spark program that has a special input format connecting to a database to do this. So the question we set out to ask is, can we apply Spark to graph analytics and make it efficient? And why again, right? It's just going back to our original question, what's wrong with specialized systems? We don't want to separate specialized systems to maintain. We want to leverage sort of the existing system for there's a lot of engineering that's gone into a good engine like Spark that take care of the task distribution, scheduling, and all of those. And we don't want to rebuild all of those. And then there's engines like Spark, great for ETL. Let's just reuse Spark for ETL instead of having Hadoop in one side to do the ETL and then piping data into Giraffe. But even more importantly than ETL, I think this key part, which is actually enabling joining of different data sources with graphs. So if we can build a system, a graph processing system on top of Spark, this essentially enables joining so tabular data structures like RDD with graph data structures in the same engine. And this enables much more richer, powerful analytics you can do. And so there's a couple parts to this challenge. One is really, how do we express the graphs, the graph computation? And as Joey showed you, there's two parts to the puzzle, right? One is we need an API to actually express the graph computation model, what we call graph parallelism. And the other one is how do we actually make it fast? How do we execute graph parallelism efficiently in an engine like Spark, which is entirely data parallel? So we are introducing, which GraphX consists of a very simple primitive, a graph in GraphX, really just two RDDs. And if you've ever been to a meetup or never read anything about Spark before, RDD is basically a distributed collection of data in Spark. So a graph consists of two RDDs, an RDD of vertices and an RDD of edges. And the RDDs, the data themselves might be partitioned in a specific way to actually exploit the graph structure to improve the computation and reduce communication. But this is all hidden from the users. So from the user's point of view, there's only two RDDs, RDD of vertices and RDD of edges. And then you can apply some standard Spark-like relational operators on those RDDs. For example, we join RDDs of vertices with another RDD of some arbitrary metadata. You know, you also join RDD of edges with another RDD. And there's a key component, a computation primitive called aggregateNeighbors, which essentially takes in two closures. Lie a little bit is really another actual argument called direction. For simplicity, let's ignore that for now. So two closures, there's a map and a reduce. And conceptually, this aggregateNeighbors is essentially running what Joey described as a vertex program on every vertex, except it's running really a MapReduce program on every vertex. So the map gets applied to every one of the neighbors, and then reduce gets basically doing a reduction, aggregation on the vertex itself. And I'm going to walk you through an example right now. So let's say if you have this graph, it's really just like a star graph, and then we want to run aggregateNeighbors. What's going to happen is I'm going to run map on each of the neighbors. So this is taking the view to the perspective of the vertex A. I'm going to run map on B, C, D, E, F. And then for the results of those, I'm going to send it to A. And A is going to run a reduce on that to aggregate and then update the value. So this is a little bit abstract still. It's not much better than the math Joey showed you. So that's it was actually a real example, which is just calculating the vertex degree. How are we going to, in case you missed your introductory computer science class, the vertex degree is defined as the number of edges that's connecting to the vertex. And in this case, let's ignore directions for now. So the way I would count vertex degree for every single vertex in my graph can be easily expressed with aggregate neighbors by defining the map function as just always returning the number 1. And the reduced function is simply a sum. So when you run this, you're going to run a map function, which is 1. Going to get the result 1 on B, C, D, E, F, each of them getting the number 1. It's going to set number 1 to A, and then it's going to run the sum of all those numbers and return you a result 5. So conceptually, and once you run this sort of conceptual MapReduce program on every single vertex, you get the results. So A has 5. I missed an edge there. All right, so somehow my graph screwed up. But in this graph, everyone else should really have the number 1. So A have a number 5, B, C, D, E, F should also, all of them just have degree 1. And so so this is actually the API we're building in GraphX, which gives you a little bit more concrete view of it. There's one, so graph is a class that consists of 2 RDDs. There's the RDD of vertices and RDD of edges. And then you can also join the vertices and edges together, which generates what we call triplets. So triplets basically contains both the vertex data for both the destination and the source of the edges. And then you could do transformations like you could filter the vertices, you could filter the edges, you can map the vertices to create a new graph, or you can map the edges to create a new graph. Then you could do joins, and then you have the finally aggregate neighbors, which is used to do computation. And this API looks very, very simple, hopefully. But you might have a question, is this enough? Like, can I express PageRank, triangle counting, or the ALS, stuff that's really hard to capture in math? Can I express them? The question is yes. So using just those APIs, we were actually able to express the Prego and the GraphLab or PowerGraph computation primitive. So we provide a similar API in a very small number of lines of code. We could build this 2 APIs. So we could build Prego API in about 20 lines of code using aggregate neighbors. We could build the entire GraphLab API in about 40 lines of code. So this is just demonstrating the expressivity of the new API by linking us to it. If we can build the GraphLab API, anything can be expressed in GraphLab can be expressed in GraphX. And behind the back sort of scene, GraphX framework is actually doing a lot more than what you think. So for example, we are adopting a lot of our principles to learn from the GraphLab project, which is Joey's thesis. So for example, we're partitioning by edges, and then we're replicating the vertices. And we always try to fix the edges to a certain partition, so we almost never move any of the edge data. And this is just to reduce the amount of communications happen. And then the specialized in memory hash indexes is built up for doing very fast joins, which are just add-ons to Spark. So we didn't have to change the Spark engine, we're just building on top of the Spark engine. And then there's even optimizer, which we're building right now. I think it's pretty neat. It basically hooks into the closures bytecode to see what methods you are invoking in the closure itself, and then choosing different execution strategy based on the access pattern. For example, if you're, let's use an example, if I'm not accessing my target on my aggregate neighbors, I can always skip the, I can skip replicating my vertices by, sorry, I can only replicate half of the vertices instead of replicating all the vertices. So instead of replicating both my source and destination to all the partitions that have edges on them, I can only replicate vertices to partitions that have vertices, so edges that only has a destination. Oh, this is really hard to explain. Talk to me offline about this one. So we have, it's right now, a lot of the GraphX implementation done on top of Spark. we also provides both the GraphX Prego abstraction on top and build a collection of standard algorithms on them, including PageRank, connected components, and all of those. And they will be released soon-ish as part of Spark 0.8. But let me actually do a demo. So how many of you have actually tried a graph processing framework before? GraphLab, Giraffe, any of those? All right, good. So this demo is going to be slightly different from the usual graph processing demo you see. I'm going to start with the Wikipedia, a dump of Wikipedia. I'm going to do ETL in the console, and then I'm going to run PageRank on a subset of the graph. And it's not exactly easy to do ETL, so I try my best to actually type the stuff. Oh, wow. It was wrong. That doesn't work. It's okay. I just. Does that work? All right, so I have a Scala console here, and this is really a Spark shell. Oops. So I launched about 5 new Spark cluster. For those of you who are new to Spark, this is using just the Spark EC2 script to launch this cluster. You can do it yourself in 5 minutes. And then, so I have a cluster here, and I previously had a screen session, which hopefully is still up. Okay, here we go. And let's just quit this. So what I'm starting is the thing called Spark Shell, which is a modified version of the Scala shell. And in case you didn't know before, so Scala is the language we chose to implement Spark on. But in addition to Scala, we also provide APIs in Java and Python, so you don't actually have to know Scala to do the data analytics on Spark. And in this demo, I'm going to use Scala. I think for those of you familiar with Java and a little bit of functional programming, you should be able to understand most of the stuff, even though the syntax might seem a little bit unnatural to you. So this is a Scala shell, or the Spark shell, which is a modified version of the Scala shell. The way we modify the Scala shell is we actually capture the bytecodes compiled by the Scala compiler, and we ship those bytecodes directly to all the workers. So you can actually run distributed computation in the same console for a program like Spark. And you could define, for example, showing a variable or a constant really, called a, and then you could evaluate expressions like a+1, just give you a result 2. And I'm gonna start. Actually, it's a little bit hard to type. I'm just gonna copy paste. So what I'm doing here is first I'm gonna import the GraphX APIs, so it's just importing Spark .graph package, and underscore is a wildcard that imports everything in that package. And then the second thing I'm doing is I'm defining a hash function that basically takes in a string, makes everything lowercase, get rid of all the spaces, and generates a hash code. And this is what I'm going to be using this page hash function to generate Vertex IDs based on based on the titles. So next is I'm going to create an RDD. In this case, it's a wiki, the RDD name wiki, and it's pointing to a bunch of text files on HDFS, which I pre-downloaded a collection of Wikipedia raw text dump. And we could take a look at what's actually in there. So for example, if I do a tick 10, it's going to return me the first 10 lines in all those files. So right now it's going to launch a task fairly quickly, and it might be a little bit hard to see, but basically take 10 returns an array of 10 elements. And the first element is this thing called accessible computing, and then there's actually a tab here, which is not very clear to you, but right after accessible computing is a tab, and then it says redirect to computer accessibility, and then there's some sort of, I don't know what's that apart from camel cases. But if you go to Wikipedia,
That's not JSON, is it?
This is not JSON. This is the Wikipedia markup.
Oh.
Yeah, if you edit Wikipedia, this is essentially what you actually see. There's two kinds of dumps. The other dump Wikipedia has is the XML dump, which I showed a little bit earlier, but this one's a markup dump.
Can you download this file?
Yeah, anybody can download this. It's freely available.
And it's a format, a compressed format.
I don't remember exactly, but I think so. It was busy to compress. Don't quote me on that. So if you go to Wikipedia and then go to this page called Accessible Computing, you realize it gets redirected to computer accessibility. So this is actually, I'm not lying, this is what's Wikipedia text. And if you look at this, really, every line is one article, and each of the article name or the article itself is a vertex. And then there's links here that's denoted by the square brackets are really edges in a graph. So what I'm going to do next is I'm going to generate a graph out of this Wikipedia dump. So let's first, tab-separated files are not exactly easy to work with. So let's actually define a class called article so it's easier to work with. So I'm defining basically a new Scala class, which is the same as a Java class. And there's two fields. There's a title field, which is string, and there's a body field, which should contain the body of the Wikipedia article. It's also a string. And then I'm going to create an articles collection, which, so what I'm doing here is I'm taking the raw Wikipedia dump, and applying a map. So map function gets applied to every line of the raw dump. So I'm basically, for every line, I'm splitting it by tab. And then for some of the data in the Wikipedia text, they actually don't have the body field. So this is just like real world data that has missing values. I'm basically filtering those out. I'm only looking for the articles that actually have the body field. And then I'm creating an article for every line. So the first part of the tab separated file is a title, and the second part is the body of the text. So this way I created a new RDD called articles, which contains basically all the articles in this article object. And then I'm going to create vertices, except I'm applying a filter here. So what I'm doing is I'm taking all the articles, I'm looking for the data that actually contain the word Berkeley in its title, and then I'm going to create a vertex. And in this case, if you take a look, so the vertex consists of two parts. There's the ID of the vertex, and it's the user defined data for the vertex. And the ID here is just a page hash of the title, and the data is just the title itself. And the next part is the most tricky part, which now I no longer have to type. What I'm doing here is, remember all those links, they're basically denoted by square brackets, two square brackets. So I'm just defining a regular expression pattern here, like this. So this is graphing for everything that has two square brackets and with any arbitrary text in between the closing square brackets. And for every article, I'm going to use this pattern to actually find all those square bracket links. And for every link, I'm going to create a new edge. And the source ID is just the hash of the current page title, and the destination ID is the hash of the links I just found. And I'm just assigning an arbitrary data value 1.0 to the edge. So this will create me an RDD of edges. And next, I could basically create a graph now. A graph is very simple. It just takes two arguments. It takes the vertices and it takes edges. And you can create a graph. Except real-world data is, again, not very clean. And in this case, in Wikipedia data, a lot of edges actually point to, so humans make mistakes when they edit Wikipedia, and a lot of edges point to pages that does not exist. So it's giving you a 404. It could be problematic when running PageRank. We basically keep pointing to, for example, vertices that actually does not even exist in graph. So we have this cute little method called correct edges, which will essentially clean the edges for you. So only it filters out all the invalid edges and only finds you edges that's actually valid. In this case, it's only finding edges that points to any pages that contain the word title Berkeley. And it's actually there is a valid page for on Wikipedia. And then, last but not least, we're going to call the similar trick for Spark RDD called .cache, which tells GraphX to actually try to put this data in memory. So we can do repeated analysis very quickly. So I'm going to create this graph. It takes a couple seconds to actually filter and clean the edges. As you can see, there's some sort of status message. All right. So now I've created a graph called G. It's really just a graph and have two types. There's a string and double. The string is basically the vertex data, the user defined data, which are just titles. And then the double is what we pass, the arbitrary 1.0 we pass to the edges. And now we can run, for example, graph analytics algorithms like PageRank. Whoops. So what I ran was just var ranks equals, we have this analytics package with a number of common algorithms already defined in them. And I'm passing a graph and running PageRank for just 3 iterations. And I'm going to run the results. Which, because remember in Spark, everything is actually lazy. So this is inheriting from the RDD idea of lazy evaluation. So really nothing happens here. I've just composed a new graph called ranks that will have a lineage pointing to how I'm going to compute the ranks. And now, let's see how big the graph is. You're probably very curious. So because I'm doing a count, and I'm actually referencing the vertices, this is going to trigger a computation. It's actually going to run PageRank along with some of the filterings we defined before. And so this is actually the most time-consuming part of the demo, which might take, I think, half a minute. What it's doing here is launching a number of rounds of tasks and running PageRanks in a number of iterations. So while it's running, what I'm doing is running PageRank on all the vertices that contain the word Berkeley in their title. Which page do you guys think would have the highest PageRank? Anybody? UC Berkeley. All right, UC Berkeley. That's a good guess, and that is right. What about the second rank, second highest ranked pages? What, Stanford? So you've been. Any more guesses? It's actually a nerd's favorite. I think my demo just failed. Something is wrong. Maybe I lost my connection. Nothing is responding anymore. Oh, well, failed demo. Yep, now we actually know it's not Ken. So what I'm supposed to show you, this is embarrassing, but what I'm supposed to show you, if this ever comes back, I don't think it will, nothing is happening, is you get the result back, and again, basically a new graph. Everything's working funky today. So you get a new graph with the, each of the vertex data is essentially the rank of the pages. And then you could, for example, what I'm supposed to show you next is actually going to join the new graph, which consists of the ranks. So I'm going to join the ranks graph with the original Wikipedia graph. And using that, I'm going to actually fetch the highest ranks pages based on their title and print it out nicely on the console here. Let's see. Yeah, I think something else is, maybe the screen died.
Just doing it. Copy and paste it all in. Yeah, you can connect to the screen.
Well, screen's responding, but this particular screen is not. Let me see. All right, let's see what happens if I do this live debugging. Spark shell. Right. Let's just run this whole thing. Right, let's see hands again. So I am running on a little bit of lesson for you. I'm actually running on a bleeding edge trunk for Spark. And if there's a bug here, I'm basically betting my presentation on that. Hopefully, it doesn't happen again. Otherwise we'll be filing bugs today. This demo used to run a lot faster, I guess. Oh, but that's not. Let me just run through the last one.
Number 2, Berkeley Unix.
Almost. There's another project. Berkeley DB, yes. So number 2 is actually Berkeley DB. If this ever finishes running, you'll see that.
You're trying for Stanford?
Pretty slow. So I haven't tried for Stanford yet. So the reason it's actually the Wikipedia graph is actually pretty sparse. The graph is actually pretty sparse. So if I try to emulate the Mate demo, which you might have seen before, which is testing how many pages on Wikipedia contains the word Berkeley and how many pages contain the word Stanford, you might actually get no hits for a different school if it's not Berkeley. So I didn't want to show you a demo. All right, here we go. So as you can see, UC Berkeley was the highest ranked page, sort of what you would expect, and then Berkeley DB is second highest ranked. And then there's a bunch of other pages. Because the graph is so sparse, it's actually hard to get ranks from them just by running 3 iterations of PageRank. You might have to run more to actually have ranks. They all have the standard default rank of 1.0 right now. So despite the a little bit problematic demo we had, I'll answer your question in a minute.
Quick question, what's this, how many vertices were there in this computation?
So this was just running on, I think, 10,000 vertices. So actually, most of the time here, it's actually done in ETL. It's not even processing, running PageRank. It was just processing those gigabytes of data to generate the graph.
Meaning uploading those to memory.
Meaning reading them into memory, putting it into the format of vertices and edges, and then doing the regular expression graphing. Yeah. So, but what I'm trying to convey to you is when this project is mature enough to get released, and we actually don't see hands anymore, which I actually don't think it was the problem of Spark or GraphX. It's probably screen. This process used to take days. You have to write fairly complicated jobs in a variety of different languages, and then you have to write a workflow manager to connect things together, and you deploy a specialized system to run PageRank, for example. Now you can do it in minutes, literally. So I actually typed this in the console yesterday in like minutes. It's hard for me to type that right now, but it's fairly easy to express. It's thanks to the capacity you gain from building a system on top of Spark. So back to the presentation. So GraphX is essentially a graph parallel, exposes a list of graph parallel primitives on top of Spark. And then right now the performance is actually not as good as what we like yet. We're working on improving the performance. But the real key, I'll get to Q&A in a minute. So the real sort of key killer app, I think here, is you don't need to have different systems or different parts of the graph processing pipeline. You can do the whole thing in a single one and it enables joining the data as graph data with normal tabular relational data. And we are finalizing the APIs, so you could actually find the current API by following this link, bit.ly/graph-API. And it links to a GitHub, basically source code of the graphs.scala file. And we are looking for feedback on improving the API itself, because I think it's very important to get it right. So once we release it, it's hard to change. And we are still actively working on improving the performance of the systems. You will be part of either Spark 0.8 or 0.9. And so in the broader umbrella, this is part of the Berkeley data analytics stack, which centers around the central component of Spark and a lot of other components building on top. I'm sure you have heard about some of them already, and you'll be hearing more about them in the future. Thanks. And questions? Any questions? Yes.
So you said the graphics are a little bit slower than GraphLab.
Yeah.
I'm just wondering, like, how much was the ratio?
Yeah, so we did a, I wonder if I have that slide. So the question was GraphLab here. So this was 2 weeks of work when we started the GraphX project. We haven't really measured the performance again since then. So we're going to do that more in the next few weeks. But when we spent about 2 weeks working on GraphX, this was running PageRank on the live journal graph. So it has like 200 million edges. So it's like a reasonable graph. And it's somewhere between GraphLab and Hadoop. We haven't done more performance studies. This is a sort of work in progress. So, if you want to ask me how I can improve performance, I can tell you. I'm happy to tell you more, but don't ask me how does it compare with X. We haven't done those yet.
What are the major issues in performance you're seeing?
Right, so the major issues in performance, a lot of them are iterative computations. A lot of the graph computation essentially gets transformed into joins. And when they are iterative, every join we're basically rebuilding hash indexes to do the join. And we think a lot of time ended up in the whole pipeline becomes just building those indexes. So we can actually just build the index once and then reuse them in the future because everything's in memory. At least all the vertices in memory anyway. And then there's parts about we could, this is the part about the really hard thing to explain, which was we could actually look into the bytecode of the closures to see what the access patterns are. And then based on that, we could reduce the amount of communications. So all those tricks, we haven't had a lot of time to actually apply them yet. We do them.
So conceptually, you can think of it as the system GraphLab, the way it works is when you define these operations, you get to see the full triplet always. And if the user-defined function, these aggregate neighbor functions, don't care about the vertices or don't care about edge attributes, we don't have to have that data available, which means we don't have to materialize it. And so if you can actually look in the bytecode and figure out what you access, you can drop parts of the data and reduce data movement and in-memory storage.
That's an excellent answer. Hopefully you got more out of that than...
So, quick question about this chart. Is it the runtime for Hadoop? Is it the number of milliseconds per CPU of CPUs, or is it the total runtime?
This is a total runtime in seconds. In seconds, yeah.
So,
Running 10 iterations of PageRank.
So if I understood the computational model right, it's essentially based still on the Pregel model, but the advantage that you get over Hadoop is that you're running it in memory. Or are you also trying to sort of incorporate some of the consistency and partial computation methods of GraphLab?
So that's an interesting question. So actually, what we've done, when we say Pregel, we've changed Pregel slightly to use what we've developed from GraphLab to make the Pregel representation faster as well. So essentially, we've mapped it all to this Vertex cut model for data representation, which allows us to distribute individual operations for a single vertex across the entire cluster. We only support a synchronous execution model right now in GraphX, which GraphLab has one big advantage that it can execute fully asynchronously. For a lot of computation, the synchronous model is good enough. It's not as efficient, but it might be easier to debug for some settings. So I think it's a good place to start. In the long run, it'd be neat to look at asynchronous, adding sort of asynchronous properties of GraphLab into GraphX, but that would require changing the way we look at Spark as well. or at least right now it seems like that.
From what I understand, a significant portion of the performance and advantage comes from how the Vertex is cut initially. So what are the implications of that for a dynamic graph? Like the data sets and the graph, the result sort of it changes a lot.
That's a great question. So what is the implication of a changing graph on the partitioning model we use? So it actually turns out the partitioning model we use is extremely simple, and it requires no communication. Essentially, it looks like random partitioning, but we're going to partition in what amounts to a 2D grid. So we're borrowing a technique from scientific computing, which basically means when I pick up an edge, I can look at the IDs of both those edges and assign it to a family of machines that's going to reduce the overall amount of data I'll have to communicate. Which means that when I look at a new edge, I can, on that edge alone, make that decision. So a streaming graph is just adding more edges to this representation. So it should work, although we don't have a streaming version up. So
just on that, is that like a consistent hashing?
it's sort of like consistent hashing. You can think of it, the right algorithm is 2D partitioning from sparse matrix representations.
Have you matched this to a storage format, so an underlying persistent store of some sort? There's probably quite a few that you could have done that with.
We have not. That's a great question. So for graph databases, which is a very big emerging area, we operate on HDFS. Actually, I don't know if there's any, you want to talk about bindings for Spark?
So really, because the expressivity of Spark, you could run arbitrary programs. So you could write a very simple program that inserts everything to a database. You could write a simple program that converts everything to any arbitrary data format you want. So it's fairly easy to do those. And we always welcome open source contributions. Yes, Peter.
So what sorts of things would you see if your memory is doing, essentially, if the size of the graph is bigger than the...
Yeah, so we are starting, so it turned out you can actually fit a lot into memory. We are starting with the putting everything in memory for our first version, but it turned out in our design the edges access sequentially, which are really sort of the bulk of your data. So you could put edges on disk. You could put edges on disk and just put the vertices in memory in sort of the optimized hash form we talked about earlier. And then you need random lookups on vertices, but you could do edges sequentially. So now the entire graph needs to fit in memory.
I was wondering about sort of the vision of the project. I mean, you made a very compelling case about the whole ETL pipeline, but then you could have also loaded that into GraphLab and sort of, just said, GraphLab, you guys are doing good work. You continue to do good work. What's sort of the vision? Why do you think there's something else needed that goes beyond, or is there something beyond that, or do you just want to make it easier for people with one tool chain?
So Joey and I might have very different visions. So how about I try and answer this, and then I'll pass it on to Joey. And then let's see what the two sides of the coins are. I think part of it is just for the people here. The users of Spark might like to do graph computation. You already have Spark up and running, and you really want to do some quick prototyping. It's a pain to actually port to a different system. And then I could just do it easily in this whole, the same Spark system, even in the shell. In the longer term, I do think we can catch up in performance to GraphLab. It might not be as good because GraphLab is a very well-engineered piece of work. But if it's good enough, all right, I'll pass it on to Joey.
Right, so I have a tricky time answering this. So I actually have a startup around GraphLab, which is trying to take that platform and be able to really do large-scale analytics. But we're really focusing on graphs, and by really focusing on graphs, we're able to get performance that's going to be hard to catch up to, although we'll keep trying for the GraphX project. But at the end of the day, I actually think it's kind of a neat opportunity for projects like GraphLab, that we can use this sort of technology in the pre-processing, post-processing phase, and then swap out the calls to graphs to our much more advanced system to process the internal graph operations themselves. And so it kind of lets us blend systems together. So I think it's an opportunity to sort of combine the two views for both systems.
I used to see references on the Spark project about a project called Bagel, supposed to be graph processing. Did that morph into one of these? Yeah.
So when I came in, I started looking at Bagel as well. Bagel is basically a Spark project to emulate the Pregel model. But it very closely emulates Pregel, and it turns out writing PageRank is substantially more complicated when you really closely emulate Pregel. And the abstraction we put together here brings what was probably like 100 lines of code down to 4 lines of code for PageRank. So at the end of the day, I think we're going to continue to expose the Pregel API, but we can do that on top of this system and make it run more efficiently. So this is what PageRank looks like when you switch to this API. So it's literally 4 lines for the code itself. So this is the program. And most of the programs we've written actually look like that. You're just changing the way you look at your neighbors and the way you accumulate that result. So I think, in the long run, I think this will replace the way you operate with Pregel.
That's good. Any other questions before we break off to the offline hard questions? All right. Thanks for coming. And